Welcome to this presentation about graphics performance and best practices. My name is Kalland. I grew up in the Oslo area and I studied mathematics and informatics at the University of Oslo. I got a master's degree in applied mathematics in 2008, and since then I have been working for Qt development frameworks in Oslo in the graphics team. I have mostly been working on OpenGL related things, and currently I'm working on the QML scene graph. And if any of you know the demo scene, I'm also a demo scener. If you have any questions during the presentation, you can just ask. Just raise your hand and someone will be around with a microphone. Please wait for the microphone. My goal for this presentation is that you learn something or get some ideas on how to improve your application performance. Hopefully that will make your application snappier and your users happier. And down the line there will be profit. In this presentation I'm going to cover briefly graphic systems and paint engines. I'm going to say a couple of words about pixel formats. And then I'm going through strengths and weaknesses of the OpenGL and Raster paint engines in more detail. And I'm going to go through some of the features one by one to see how the features affect the performance. And in the end, I'll go through an example of an example program where we go through some steps how to improve the performance of this example. So who of you use a different graphic system than the default? So only a handful. Okay. The graphic system defines what kind of surface you get for your widgets and your pix maps. You can set the graphic system three ways. You can use the command line argument graphic system, or you can use an environment variable called Qt_graphic system, or you can set it in your source code by calling Qapplication set graphic system. We support a few different graphic systems. One is Raster, which is a cross-platform one. In this case, the surface is placed in system memory. If you use the OpenGL graphic system, the surface is placed in graphics memory, so you get an OpenGL context and a swap chain for your widget and a texture for your pix maps. And we also have native graphic systems, which are system-specific, and we let the system decide what to do with the surface. We recommend using the Raster graphic system. We have seen that the paint engine that is related to the graphic system supports all the features, and it is often faster than using the native one. The OpenGL graphic system is experimental, and I do not recommend using that. Instead, I recommend using the Raster graphic system and the OpenGL paint engine explicitly. So the paint engines define how to render to the surface. So it implements functionality used by the Qpainter in a way that makes all the surfaces look the same from the painter's point of view. The paint engine depends on the type of surface you're rendering to. So widgets and pix maps, there the surface depends on the graphic system, so the paint engine also defines on the graphic system. If you use a QGL widget, you always get the OpenGL paint engine, and that's the way I recommend using or getting an OpenGL paint engine. If you paint on an image, you always get the Raster paint engine, the Qt's software rasterizer. For the rest of this presentation, I'm going to use the Raster graphic system always, and then I'm going to use the Q widget to get the Raster paint engine, and I'm going to use a QGL widget to get the OpenGL paint engine. And I forgot to mention it on the previous slide, but the Raster paint engine is actually the default on Windows, and it is going to be the default on Linux from 4.8, Qt 4.8. The Raster paint engine supports various pixel formats, and not all of them have the same performance. And we recommend only using RGB32 and ARGB32 pre-multiplied. And you notice that this does not include the ARGB32, which is not pre-multiplied. That will the ARGB32 and all the other pixel formats will degrade performance. And I have tested this with a simple example where you just blend one image on top of another. And I've seen up to 80% performance loss if one of the sources, either the source or the destination is not a recommended format, and up to 90% if both are different from the recommended format. The reason all the other pixel formats are so slow is that Qt's native pixel format is ARGB32 pre-multiplied. So in general, all the other paint operations has to go through this format. There are some optimizations for other formats like RGB16 for some of the paint operations, but not in general. So for instance, in this example, I'm going to blend one image on top of a destination image. And what happens is that for each scan line, we're going to, in the destination, we copy that scan line and convert it to ARGB32 pre-multiplied. Then we copy an equivalent line or the corresponding line in the source. It does not need to be horizontal like in this example. It can be at an angle. But we copy it out. We convert it to the common format, ARGB32 pre-multiplied. Then we blend this source line on top of the destination line, and then we copy that, or convert it and copy it back into the destination. So if you want to improve this performance, you want to use ARGB32 pre-multiplied, because then you can avoid this conversion, and you can do the operation directly in the destination. And now we are going to compare OpenGL and the Raster paint engine, and I've listed some of the benefits and drawbacks, or the benefits of both of them on this slide. I'm going to cover feature by feature afterwards. So in Raster, you get all the features. The OpenGL paint engine is also quite feature complete, but it does lack some composition modes like what is it? Overlay and color dodge and all those strange composition modes. Raster also has the benefit that it doesn't require multi-sampling when doing anti-aliasing, so it doesn't draw more memory, and you can toggle anti-aliasing on and off during one single frame, and then spend the CPU cycles where it's needed. While on OpenGL, you just have to decide beforehand whether you want multi-sampling, and you're stuck with that decision. Someone else mentioned another benefit with Raster a couple of days ago that I didn't list here. That's that the Raster engine supports partial updates. So if you only update parts of this every screen at a time, then you might consider using the Raster paint engine over the OpenGL paint engine. But the OpenGL paint engine also has some benefits. The GPU can offload the CPU, so you can get better parallel processing. And you can, on some devices, save battery because the OpenGL hardware is more specific for graphics, more optimized for it. And finally, you can mix OpenGL painting with your own OpenGL code so that you can use a Qpainter on top of something else you have rendered with OpenGL, for instance. I'm going to cover some feature by features now. I've compared OpenGL with Raster directly with an example that looks like this. I can run it as well. So it looks like this. You can jump around a bit, walk on water like Jesus. And you see a frame rate counter to the top left. So this example is quite optimized for Raster, the Raster paint engine. All the pix maps are just one-to-one pixel mappings. There's no scaling or rotation. There is no anti-aliasing and no smooth pix map transforms. And yet you see on 3 out of 4 configurations, the OpenGL paint engine performs better than the Raster paint engine. So I would say that the OpenGL paint engine usually performs better than the Raster paint engine, but it depends on the use case and you need to try for yourself. When it comes to anti-aliasing quality, the Raster paint engine is better. The Raster paint engine has 256 different coverage values. So in this illustration, you can see 256 different gray values along the edge of this dashed line. On OpenGL, on the other hand, you see that, if you're able to see it in the close-up here, you see that along the line you have fewer gray values. And you typically get 4 or 8 different coverage values in OpenGL if you use multi-sampling. Then I've written an example program to compare anti-aliasing speed. It looks like this and this. Oops, not close that one. It's not that interesting to see it in action, so I'll just leave that. If you run the Raster paint engine, you can see on this left graph that the anti-aliasing performance depends on the shape. So the curvy shape has much worse performance than the blocky shape. And this has to do with the number of spans you get. So if it's a complex shape, you'd get a lot of different gray values, and you get a very suboptimal rendering path. Well, if you have a blocky one, you'd have a lot of pixels with the same value, and you can just do some fast rendering there. With OpenGL and on this hardware, you see that you pretty much get the constant hit on performance. The performance hit you get when using multi-sampling depends a lot on the hardware, and in this case we are using integrated graphics, so this is why you get this bad performance. And I've seen up to 75% performance loss on this hardware with multi-sampling. On other hardware, it might not make a difference at all. Stroking is not very optimized in the Raster paint engine, at least when it's anti-aliased. So when we generate strokes, we generate a complex painter path that we then fill. And with that you can lose a lot of performance because, as I mentioned in the previous slide, the complexity of the fill affects the performance of the anti-aliasing. So you lose 85 or 92% if you can see those numbers when rendering this image or this image with the Raster paint engine. On OpenGL, the stroking has been optimized to generate triangles directly, and there is almost no performance loss. And that's because the bottleneck is not really the GPU in this case, but rather the generation of strokes. Then I have written a program to test among other things, bilinear filtering speed. It looks like this. I can run this. So I can turn smooth pixmap transform on and off. I don't know if you noticed the difference. The bug becomes a bit blurrier with smooth pixmap transform, and I can rotate it in 2D and see how that affects the performance. So with bilinear filtering in the Raster paint engine, you don't lose that much performance as long as you don't rotate. As soon as you start to rotate, the performance loss is quite dramatic. And this is because the non-rotated version has been optimized. In OpenGL, bilinear filtering is for free, as you can see. The hardware has this built in, and it costs nothing. So if you want this feature, you should use the OpenGL paint engine. I've also implemented perspective transformations in that example. So you can run that again, see how that works. You can use a 2D transform or a perspective transformation and see how that affects the performance. On Raster Paint Engine, you get pretty good performance when you're just rotating. That is without bilinear filtering. As you saw in the previous example, with bilinear filtering, the performance drop is significant. But this benchmark was run without here. But as soon as you do perspective transformations, you get a significant performance loss. And this is because it goes through a more general code path, and it is not very optimal, as some of you have experienced, I'm sure. On OpenGL, this is not a problem. Perspective transformations are just a standard 3D thing, so that is what the hardware is made for. And there is clipping performance. I'll show how that looks as well. I have can specify the clip here, a rectangular, round clip, or a ridiculously complex clip. Now, as you can see in the Raster Paint engine, for the simple clips, you get a small performance boost. It's not because you get the performance boost in general by using clipping, but it's because you're rendering fewer pixels in this case. So remember that clipping is not for free, but in this case it looks like it is for free. But just to make sure that the message comes through, I have added a complex clip here, and you see that the performance is much, much worse with a yellow bar there. In OpenGL, the performance loss for a rectangular clip is, well, you don't get a performance loss with a rectangular clip. This is the purple bar, the second purple bar from the top on the right side. But as you can see, the red bar is a bit lower, and the purple and red bar on the next under rotate are lower. And that's because the rectangle has been rotated, so it's not from the graphics, from the paint engine's point of view, it's not longer a rectangular clip, so it has to go through a different code path and use the stencil buffer, which requires some pixel fills, which takes time. And as you can see, the complex clip is also quite bad with the OpenGL paint engine. Next is gradient performance. In the Raster Paint engine, gradient performance is not that great, and it gets worse the more complex your gradient is. So for the conical gradients, the performance is, well, almost gone completely. OpenGL, on the other hand, does not have this problem because it has quite much power per pixel. So if you need a lot of gradients, you should use the OpenGL paint engine, or another option is to render the gradients into an image or a texture and use that instead. That is much faster. I can show the example running. So I'm comparing this to a solid fill just to have something to compare with. Well, these numbers are not exactly as in the slide because it's on different hardware and a different system. So as you can see, the performance drops from about 400, 500 to 150 with a linear gradient. On the positive side, though, if the linear gradient is perfectly horizontal, it is as fast as a solid fill. Now, the radial gradient was slower in the slide, but that slide was based on Qt 4.7, and this right here is running on Qt 4.8. So a colleague of mine made an optimization in Qt 4.8, which makes the radial gradients faster than linear gradients, making one of my points moot. And the conical gradient is quite slow. I have also made a comparison with texture fill, just to show that that is actually much faster. So it is actually worth rendering the gradient into a texture and use that instead if you need performance. Then there is something that is related or very important for OpenGL, state changes. I've written an example that looks like this. I can run that one as well. Or I should run it with one of the parameters. Fast. It's a bit small, but it's a keyboard. It's quite crude, but it kind of works. I've implemented 3 ways to render this keyboard. In the first example, I render the keys individually. So I render the background, the rounded rectangle, and then the text on top. Then I move on to the next key and render the rounded rectangle and the text on top. And the next way of rendering is to render all the rounded rectangles first, then all the text on top afterwards. The idea is that I want to reduce the number of state changes, like setting a pen or a brush. And finally, I've split up the rounded rectangle. I've split the fill and stroke. So I render first all the fills, then all the strokes around those fills, and then all the text on top. In code, it looks like I do more, because you first have to set the pen to no pen, and then the brush, then paint all the rectangles, then set the pen, and set the brush to no brush, then render all the rectangles again. But as you can see, both with Raster and OpenGL, the performance goes up. And that's because the state changes in the underlying paint engine are fewer. And as you can see, it is also much more significant on OpenGL than on Raster. Then we are going to look at this game example. The artwork was downloaded from Lost Garden and done by Daniel Cook, just to make that clear. So we have a bit of code here. It looks a bit overwhelming in this beginning, but this is the code. I will go through it in detail. And this is the essence of the painting code in the game that I showed in the beginning. So first you have the game class, which inherits QWidget. Then you have a paint event, which is calling paint tile for every tile it is going to render. Oops, sorry. And it stores the tiles in images, 60 of them here. Then it has a class which contains the level information and a class containing the character information, the player character that you can move around. Then there are some timing variables that I skipped here to make things clearer. In the constructor, I load all the textures one by one. In the paint event, I calculate the position of the character to make sure that it is rendered correctly, like in front of some of the tiles and behind some of the other tiles. So this is the tile position. Then I iterate over every row and layer and column in the level. And if the tile is not empty, or if it's not occluded, I paint the tile. I calculate the position on screen, and then I paint the tile. And if it has the same position as the player character, I render the player character here as well, by calling paint tile with the image of a boy. In paint tile, I just call draw image with a source, a destination rectangle, and the source rectangle, and the correct texture. Now, if I run this game example, this is an unoptimized version of the game. Now it has a performance of 43, 44 frames per second. It's not very great. So the question is, what can we do with this code to improve the performance? Do any one of you have an idea? Who has an idea? Yes. Can we get a microphone back there?
I think for the beginning we should use QGL widget.
Yes, that is one. That's a good idea. We can. So I have this one. You can use a QGL widget. Then in the constructor you initialize a QGL widget instead of a widget. And that's all the things you need to do there. Then you get this code, and we can try to run it with OpenGL. Well, that's much better. 90 FPS. Can still move around. Any other ideas?
Use Qpixmaps instead of Qimage?
Yes, actually that is a good idea if you use the Raster paint engine, because then you are sure that you get the most performant pixel format. But in OpenGL, both images and pixmaps are cached as textures. So in this case, it doesn't make sense. Oops, sorry. But in this case, it doesn't make a difference, but we can do that anyway. So it looks like this. It actually makes another optimization easier, so it actually makes sense later. So then you draw a pixmap instead of an image. So who has more ideas? No more ideas? There are a few more things that can be done. For instance, does it make sense to iterate over every tile in the level? I don't think so. We can do some, oops, that was not the right key. That was the right key. We can calculate the leftmost column and the rightmost column and just render those. Now, if it actually helps is a different thing. On different computers, different things make a difference. So this would enable that code. Well, you get from 90 up to 100. So that helps a bit. Any other ideas? I guess maybe not. Let's see what else. Okay. Okay, there's one.
I have an idea. Why shouldn't we change only the boxes where the players are moving and not the entire image every time?
Once more, you move the.
Instead of painting all the boxes every time,
Yes.
we should paint only the boxes which are changed by the player move. I mean, the last position where the player was, and the current position where the player was. And maybe use a cache, big image to host the result.
But if you run this game, the entire screen changes. So what was... So you just want to repaint the area around, or do you want to cache something else around this player?
Sorry, only the left box and the right box near the player, for example. And not the entire screen.
Okay, so you want to paint the entire level, kind of, in one big cache, or?
Yes.
Ah, okay. It would be a very big one, big cache, and which would take a lot of memory, but maybe that could be done. I haven't tried it, so but yeah, maybe you could tile up the game in bigger chunks and do that. Yeah, I didn't try it, but it's a good idea. I'm not sure if you know an API we have for rendering multiple pixmap fragments with one call. There is a Qpainter draw pixmap fragments that we could use. Then we can use just one paint function instead of iterating through all the tiles and render them one by one. To enable that, we first have to use a texture atlas. So instead of using 60 pixmaps, we use one pixmap, and we load just that, and all the tiles are contained within that texture. So instead of having the source rectangle at origin, we have to offset it by the previous position in the 2D array, and I can maybe show the let's see, show the atlas as well, how it looks. What is the best program to watch in an image file? So the atlas looks like this, basically. All the tiles are there. Yes. So that's the first step, and the next step is to actually use this API we have. So first we define a vector to collect all the pixmap fragments. And then in the paint event, we set it to resize it to 0. And then we call all the paint tile function. And instead of actually drawing the pixmap in the paint tile function, we just add it to the list of fragments, pixmap fragments. And then after, after collecting all the fragments, we just call draw pixmap fragments. This doesn't always help performance, but we'll see if it helps this time. I enable this with atlas and pixmap. I think I just missed something. either that or it didn't help in this case. Let's see. Yes, batch. It's the same. Okay. As I said, it doesn't always help. But it is worth noticing as a trick, because sometimes it can help a lot. It depends on where the bottleneck is. So if the bottleneck is the number of draw calls, then this can help. If it's somewhere else, like pixel filling or state changes, it won't help. There is one more thing that we can do with this code. If you remember the texture atlas, a lot of the pixels are completely transparent. So we are rendering a lot of completely transparent pixels. So what we can do is to actually calculate a bounding box, a tight bounding box around all the graphics, like the graphics for each tile. And we just render that smaller rectangle. So we enable this with a T. Let's see what changed. Yeah, this is the part that changed. We changed the fragment. Maybe I should remove the batching to make things clearer. Let's go back a bit. Okay, I removed the batching because that was making things a bit hard to read. But if we now enable this bounding box thing, instead of using a full source rect, we use a source rect that is a tight bounding box around the tile graphics. Now if we do this, I really hope we get better performance this time. Let's see. I call this trim. Well, we got almost 20 more FPS. And I also want to try the batching again. This time it helped. Now we got over 150 FPS. Yeah, so those are some of the things you can do with this code to improve the performance. Just to give you an idea, and hope this will spark some imagination. So to summarize, you should avoid the slow pixel formats. So you either use a Qpixmap to always get the best pixel format, or you can convert your image to ARGB32 pre-multiplied or RGB32 after loading them. You should minimize state changes, especially if you are using the OpenGL paint engine. Try to reorganize your code to minimize the state changes. And if necessary, you separate the fills and strokes. The next one is a bit obvious, but it's not always people are aware of this. Don't paint the invisible items. Especially with OpenGL, there is no culling happening on the paint engine side, so it is actually shipped all the way to the GPU. You should cache complex drawing in images or use artwork. For instance, when you saw the gradient performance, it can help. Trim away transparent parts of the artwork. There's no point in rendering completely transparent pixels. Even on fast OpenGL hardware, it does slow down. And don't clip unnecessarily. We have seen some people in QML, for example, it's very easy to just set the clip property to true, and you always get this nice clipping, and you do that on a few hundred items, and suddenly the performance is quite bad. I also have a few tips and tricks that I didn't cover specifically today, but you should not process the same things twice. So hold on to your Qpainter paths, especially the OpenGL paint engine will do some caching to reuse when it sees that the Qpainter path is reused. Use static texts, if that makes sense, to hold on to your layouts. You should consider drawing multiple items with one draw call, like for instance the draw pixmap fragments or draw rects. That way you can avoid some state changes and especially draw calls in OpenGL. Set the opaque paint event flag on widgets if you intend to fill the entire background. And if you're using graphics view, consider using caching modes, but you should also be aware that caching modes have some drawbacks, so you have to consider the benefits and drawbacks. You should, if possible, use fewer items by combining them into one item. For instance, if you are making an on-screen keyboard, then use one item for the whole keyboard instead of using a lot of items, one item for each key. Then it is much easier to rearrange the painting code to actually reduce the state changes. Use the item has no content flag if your graphics view item does not have any content, and that avoids an unnecessary paint call. And finally, avoid the QGraphics proxy widget. It is a monster. So, any questions?
I'd just like to ask how you compute the frame rate. Is that you just print out every time in the paint method, or?
No, it calculates, or it accumulates 1 second of frames.
Okay.
And then it paints into the text into an image, and then that image is splitted onto the screen every frame.
Okay.
So it stays the same for 1 second, and then it is updated for the next.
Thanks.
I also had to disable vertical sync on the system. Anything else? Yes.
You mentioned that you can cache textures for Qimage. Is that right? Because I don't know how you detect that the image hasn't changed from one paint event to the next one.
Yeah, well, that would have to be part of your program logic. Or if you're using graphics view, graphics view will keep track of that for you. So you need to just update the texture whenever you think it's necessary, basically.
So I have to update the texture by hand, or? I thought for Qpixmaps there's some kind of Pixmap ID which you can use as a
that
cache.
part, yes. If you change the Pixmap, it will be re-uploaded. That's right.
So in the long run, wouldn't it be possible to merge Qimage and Qpixmap, because with the Raster paint engine there is no difference effectively?
Yeah, actually in the Raster paint engine, the Pixmap is backed by Qimage. So it is the same code. The only thing is that the Pixmap will use certain pixel formats. Was that an answer? Okay.
How did you calculate the tight bounding rectangle of the transparent items?
Yeah, I had to do that beforehand. So I just loaded the image and iterated through the pixels to calculate.
Okay,
and then I just stored that.
There's no call for that?
No, not right now.
Okay.
Did you try the same tests on the mobile phones, for example, on Migo, to see how it behaves?
No, I haven't tried on mobile.
Okay.
Hi. Why is QGraphics proxy widget a monster?
Yes. I was hoping I wouldn't get that question. Well, we have first of all seen that it is slow. I haven't implemented it, so I'm not sure what kind of mechanics makes it that slow, but well, it has to copy all the states back and forth, and it has to show up fake widgets and all that. Maybe the guy behind you want to answer that.
Okay, so maybe since I wrote it, I could say something about that. It got a lot better, but it's still pretty slow. I mean, one of the fundamental problems is that Qgraphics View uses one single Qpainter object, and it just passes a pointer through all the items. So the paint function inside of all graphics items gets a pointer to a Qpainter, whereas QWidgets construct a new painter inside of each of the paint events. And one of the big hacks, to call it like that, which is really hard to optimize inside of graphics proxy widget, is that it tries to ensure that the painter that the graphics proxy widget gets passed is identical to the ones that are recreated inside of the widgets that are proxied. So inside of Qpainter's constructor, there needs to be checks to see whether this widget is embedded inside of a graphics view. And if it does that, then instead of like the painter constructing its own instance, it tries to reuse the state of the one that's there already. And there's a lot of monstrous stuff inside to make sure that that stuff works really well. So it's just really hard to get that optimized. Was that good enough? Yeah.
Thanks for being here, Andreas. No? Okay. Then I'm finished.